All right, so we are on to the 2010 AMC 10A. We're now on problem 16, which was also the 12A problem 14. Non-degenerate, and before we read on, this word gets a lot of people hung up. They don't know what it means. It kind of helps if you maybe have some older family with a good vocabulary. They sometimes will refer to somebody who they don't see as a good part of society as a degenerate. So it'd be like a bad person in society. Well then, what would a non-degenerate be? Well, a good person. So if we're talking about triangles, a degenerate triangle would probably be one where the ends don't connect, because that's not really a triangle. Something bad about a triangle. Now, any triangle that's normal and the ends connect, it's kind of, what could be degenerate about that? What would it be bad? So non-degenerate must mean a normal triangle, one that connects. All of its sides connect. It's normal. There's nothing weird about it. Any triangle that does that is like a triangle, as we would call it. So don't get hung up on the word too much. Maybe think about the degenerate word and what it might mean. If you still never heard that word either, expand your vocabulary. Okay, so, but it's used intentionally because it doesn't really appear in textbooks too much. In fact, in high school and middle school textbooks, I've never really seen it mentioned. So, if you come across it, there, then that's great, but most likely you won't. It does appear in some other texts. So non-degenerate triangle ABC has integer side lengths. BD is an angle bisector. So at this point, we kind of need to start making a diagram. Because what does BD look like? We can't really see it all in our mind. So make some random triangle. Try not to make it look like it's, a 90-degree angle quite. We'll call this A, this B, and this C. And BD is an angle bisector. Here's what they don't tell us. They don't tell us that D is on AC. And I don't really know that you can solve it if it's not, though. If you try to solve it, I think there's a lot of possibilities, and really, you won't be able to apply the central concept they're getting at. I haven't come up in my mind with the reason why we know that D has to be on AC, but I just kind of assume that it is in order to solve the problem, because if I put it like over here and made this 3 and this 8, couldn't AC be shorter? I don't know. So I just went and kind of said, well, if they're calling it an angle bisector, then most likely they want us to use one of the angle bisector concepts, the biggest of which is called the angle bisector theorem, right? And we'll get to that in a moment. You can't apply the angle bisector theorem unless D is on AC. You won't be able to apply it to this problem at least. So we continue on. AD is 3. DC is 8, as it says here. What is the smallest possible value of the perimeter? So we'll call this X and this Y. And what you can do is, the angle bisector theorem basically says the following. Let's say you've got a triangle like this, and I cut this angle, and this is A, B, C, and D. Then any corresponding ratio is equal. So like left to right, A over D. That's going to equal left to right, B over C. Somebody else might want to say top to bottom, A over B, and top to bottom, D over C. And if you notice, this is the same as this. We just swapped the corners, which you can do in any proportion anyway. So we're going to apply that here. It's just that our two sides B and C are actually the 3 and the 8 this time. So I'm going to say 3 over X equals 8 over Y, and we'll cross multiply to get 3Y equals 8X. And we will say, let's say X equals 3/8 Y. Now you could have also said Y equals 8/3 of X, but I feel like it's better if we do this because 8's a little more restricting. For the simple fact that Y has to be a little bit larger for it to work out correctly. So let's say that these both have to be true, mind you. So then, because we know that the side lengths are integers, then Y is going to have to be a multiple of 8. Otherwise, this 8 won't cancel, and X will not be an integer. So assume for a second that Y is exactly 8. Let's see what that would look like if we did that. If Y is exactly 8, then X is 3, this is 11, and Y is 8. And this is where triangle inequality comes in. The two smallest sides of a triangle, and indeed any two sides of a triangle, must be larger than the third. So this sum of these two must be larger than that, and you can clearly see that doesn't happen here. So this triangle would be degenerate, right? Or at least not good in some way. Then this is not what we want. We can't use it. So we're going to have to increase y, and the next available value is 16. So if you plug 16 into y, then this will become 16 down here, and 8 goes into 16 twice, times 3 is 6. Now we have, these are the two smallest sides. They do add to 17, which is more than 16, so it works. This is it. In fact, if you were to try 24, then this would be 9, and 9 plus 11 would not eclipse 24. So this is not the smallest possible value of the perimeter with integer side lengths. It's the only possible value of the perimeter. And so we get 22 plus 11, which is 33, answer choice B. All right, next up is the 2010 10A problem number 17. A solid cube has side length 3 inches. A 2-inch by 2-inch square hole is cut into the center of each face. Before we read further, let's get a start on drawing something like what this looks like. The trick with drawing the cubes is just to make these 3 lines parallel, and then the vertical lines back here make it parallel to these 2. Right? And then the line going this way make it parallel to these 2. Something like that. Okay, so what they're saying is that there's a 2-inch by 2-inch hole cut into the face of each side. All right, let's continue reading from there. We have kind of an idea without drawing the other holes. The edges of each cut are parallel to the edges of the cube. We did that. And each hole goes all the way through the cube. So this is going to go back into the cube, right? Back that way. And come out the other side like a tunnel. What is the volume in cubic inches of the remaining solid? Okay, well, how is this going to look exactly? Let's draw one up here to get a better idea. And maybe one over here as well. Something like that, right? But the problem is this hole going through here is going to intersect that hole going through that way and this hole going through this way. So how do we approach that? Well, there's several approaches you could take. The one that I like, for example, you could find all the distances between here and the middle part of the cube that gets cut out, that intersects all the paths. You could do that. And then you could just subtract the area of that inner cube, if you will, and subtract that from the hole. But I think what I want to do is, first, the volume of the cube is 27, the original cube. Now we're just simply going to subtract that tunnel. And a tunnel is a rectangular solid, in this case. So it's the area of the base, which is 2 times 2, times the height, which is the distance going back, and that's the distance of the whole cube, which is 3. So 4 times 3 is 12. We have to subtract that. Now once that's done, this is going to come over and intersect that hole as well, going back this way, right? And there's going to be one on this side, which is not drawn, which is also going to intersect that hole. But once it hits that tunnel that we've already accounted for, we don't care about that missing space because we've already accounted for it. So we've got one of these like partial tunnels here, one up top, one on the bottom, and one over here. That is, we have 4 of those partial tunnels. Each of them have the same base, 2 times 2. And then how far in do they go before they hit the tunnel that was already created? Well, that distance, if you think about it, it's this distance right here from the side of the inner cutout to the side of the cube. And since this is 2 and this is 3, if this is centered, these are both 0.5, 0.5, which will be the distance that this goes into the cube before it intersects that tunnel. So we're cutting out this space right here, this solid, we cut out this space. What is the area of one space then? Right? It's 2 times 2 times a half, which is 2. And we have 4 of those spaces, so we really have 8. Subtract 20, get 7. That will be the answer. Okay, continuing on with the 2010 10A problem number 18. which was also the 12A problem 16. Bernardo randomly picks 3 distinct numbers from the set 1 through 9 and arranges them in descending order to form a 3-digit number. Not so bad so far. Sylvia, and incidentally, Bernardo and Sylvia appear in several problems throughout the history of the AMC. My suspicion is that they're the children of one of the test makers, or they are the test makers themselves on the committee or whatnot that decides what goes in the contest. If you happen to know the answer to that piece of trivia, put it in the comments for everybody else. Sylvia randomly picks 3 distinct numbers from the set 1 to 8. Okay, so Bernardo had 1 to 9, but Sylvia only has 1 to 8. And she also arranges them in descending order to form a 3-digit number. What is the probability that Bernardo's number is larger than Sylvia's number? Okay, so let's think about this. If Bernardo gets a 9, he wins, right? Because she doesn't have access to a 9, any number in the 900s, and descending order will be in the 900s, is going to be bigger than any number she can create. So let's start there. What's the chance that Bernardo gets a 9? You might say intuitively that it's 3 out of 9. He's got 3 chances and there's 9 numbers, so 3 chances to get a 9 out of the 9 numbers. But then you might second guess yourself like I did. And you might say, is that really accurate? Is it really going to be 1/3? Let's look at it differently. Let's guarantee he has the 9 drawn and then he chooses 2 other numbers. It'll be any 2 numbers combined with that will be the number of ways that he has a 9 amongst his 3 numbers. Out of 9, choose 3. If you calculate this and simplify 8 factorial, 6 and 2, 9 factorial, 6 and 3 factorial, the 6 factorials cancel. Flip this to get 3 factorial over 9. The 2 cancels here to give 3. The 8 cancels the 9 to give 9. So it is the same and you can feel confident moving forward. It's okay to second guess yourself and try to find another way to confirm what you believe to be true if you're not really standing on solid ground. Now, if you felt comfortable with this, great. Okay, so there's a 1 in 3 chance right off the bat that Bernardo wins. But we have to do what's left. If he doesn't get a 9, what's the chance he doesn't get a 9? It's obviously 2/3 because there's only 2 possibilities. Get a 9 or don't get a 9, and these have to add up to 1. So it's going to be the 2/3 chance that he doesn't get a 9 times the probability that Bernardo is greater than Sylvia's number if he doesn't have that 9, right? Given that he didn't get a 9. Now, you might be thinking now, well, if there's no 9, they both have access to 1 through 8, and so you can think by symmetry, he must win half the time. And that's really, really close to being accurate. In fact, if you were to do 1/3 plus 2/3 times 1/2, which would be what your guess is about this, then you would get 1/3 plus 1/3 is 2/3, and they have accommodated your mistake. They've accommodated your error in thinking. They already thought ahead making the test, and they thought, what are the potential mistakes that you might make? And this is one of the more common ones. So they put it here for C so that you will circle C and move merrily on your way, and you will get it wrong. You need to avoid that by thinking carefully. There's also the chance that they tie, and it says Bernardo's number is larger than Sylvia's. So it is related to that. You're going to have 1/3 plus 2/3 times 1/2 times the probability that his is greater than S if they have no 9 and there's no tie. So what's the chance that they tie? Well, given that Sylvia gets any particular set of 3 numbers, the chance that Bernardo matches it is 1 out of 8 choose 3 because that's the number of combinations that he can choose. So 8 choose 3 is 8 factorial over 5 factorial, 3 factorial. Observe that 3 factorial is 6, right? And 6 times 5 factorial is 6 factorial. So really this is 8 over 6 in factorials. That's going to leave you with 8 times 7 is 56. So the chance of the tie is 56. Everything else in that scenario where he doesn't have a 9 will mean they don't have the same number. And half of those values are the ones where Bernardo is ahead. So it's going to be half times 1 minus, the 1 being, we're using complementary counting right now, 1 minus the 1 out of 56, or complementary probability, I suppose, the 1 in 56 chance that they tie. Everything else is ones where they don't tie, and exactly half of those are ones where Bernardo wins. We're on the home stretch now. We're kind of rounding third. Just got to finish up the algebra. Cancel out the 2's. We're going to you have 1/3. We're going to factor out that 1/3. Don't forget there's a 1 here left behind. 1 plus 1 minus 1 over 56. That's 2 minus 1 over 56. And what would be 2 times 56 over 56? It's going to be 112. And 112 minus 1 is 111 over 56. That's what this breaks down to. Calculate it at home if you didn't follow. You could also have done it here and made it 55 over 56 and continued calculating that way. But we've got 1/3 here, and you can tell by 111 adding up to 3, the digits, that it's a multiple of 3. And in fact, 3 will go in 37 times, and you have 37 over 56. We've dodged the trap answer, we've gotten it correct, and we're moving on. Okay, and here we are at the 2010 10A problem 19. It was also the 12A problem number 17. This is a great question to watch all the way through because there's a lot of fundamental concepts in it that you really need to know that apply to many other questions on the tests. Equal angular hexagon. Pause for a second. What did I just read? Equal angular? Why didn't it say regular? Probably because it's not regular. But what does that mean then? It means it's not equilateral, but it is equal. Yes, that's exactly what it means, and you're going to have to accommodate that somehow. So equal angular hexagon ABCDEF, or a backdef if you're reading a word, has side lengths AB equal to CD equal to EF equal to 1, and BC, DE, and FA equal to R. First off, observe that these are not consecutive, right? B would connect to C as the next consecutive side, so these are non-consecutive sides equal to 1, and those are non-consecutive sides equal to R. Well, how can we do this? Before we move on, because you're not going to understand what triangle ACE is without drawing a picture. So first off, think of a regular hexagon, right? It looks something like this. Once you get the upper part drawn, the other side should be parallel to those sides, right? This isn't a perfect one. In fact, it looks horrible, but I'm going to take it. So this is kind of what a regular hexagon looks like. Then how can we make it the same thing with the angles? And what are those angles? Let's calculate really quickly. You should just know the exterior angle of a regular hexagon is going to be 360 divided by 6, which is 60, which means all the interior angles are 120. Well, then if this is equal angular, it still has to maintain the 120. So what we're going to do is extend out, say, this side, and this side, because they're the ones that have the same lengths, and see if we can do that, what it would look like. Let's make this a little bit longer. We'll keep this one kind of the same size, and this one the same size. And just so I can get a little more accurate, I'm going to come over here and draw it. Sometimes drawing when I'm not blocking the camera is off to the side. It's a little bit difficult. Try it sometime. So this looks a little bit like the Superman symbol, but that one actually comes to a point, the insignia that goes around the Superman S. So it looks something like this. The question is, where do we put the letters? Well, it doesn't really matter. I like to think in my head that 1 is going to be smaller than R. I don't know why. So I'm going to put A here, B here, C here, D here, E here, and F here. Don't get too hung up on whether it's supposed to be here or the A is supposed to go here. Just start. The longer you think about that, the more time is being wasted. And it doesn't really specify, so you're going to have to kind of figure out why this might be correct or why the other one might be correct. And usually you find that by going to the problem. So this would be 1, 1, 1, and R, R, and R. Now let's continue. The area of triangle ACE, well, let's make that A to C to E. And you might think, why, that looks almost equilateral. Maybe it is. In fact, it is. Let's figure out why in a minute. The area of that is 70% of the area of the hexagon. What is the sum of all possible values of R? So it implies there's more than one, right? Otherwise, I mean, sometimes they are tricky and there's really only one value for all possible values questions, but you can kind of assume there's probably more than one. So what can we say? First, we prove that this is equilateral. Yes, because this is 120 as we said, and this triangle, and this triangle are all congruent, so this side of their triangles are all congruent, by side, angle, side, right? So then you know that this is an equilateral triangle. Fundamental concept number 1 in the test, well actually that's probably over here. You could use n minus 2 times 180 over n for interior angles as well, but that's a little bit slow. This is faster to do 360 divided by the exterior and then subtract it from 180. So the next fundamental concept though is the area of an equilateral triangle. And the way I like to remember it is s squared root 3 over 4. I like it to be s, that's the way I learned it, and I'm going to use it. Okay, so how do we apply it? We need this side length. Well, how are we going to get it? This is the tricky part, and there's actually more than one way to do it. In fact, I bet if you looked online, there's probably 6 or 7 solutions to this problem because it has a lot of different branch-offs that you can travel down. The way I'm going to do it first is law of cosines. You might not know law of cosines yet. Learn it. And if you don't learn it, we can do another way that doesn't use law of cosines. But for now, I'm going to use law of cosines. Law of cosines starts off like this. It looks just like Pythagorean. Starts off looking like Pythagorean, but then you're going to subtract 2, take these not squared, and the cosine of the angle opposite this side. It's for triangles, right? It works for any triangle. Well, I mean, you can't always apply it, but it works for any triangle. So we can take C and call C this side CA right here. We want to know what it is. So C squared equals the two sides, the A and B are the other two sides of the triangle. So 1 squared plus r squared is 1 plus r squared minus 2 times 1, which we're not going to write, times r, times the cosine of 120. If you don't know how to quickly calculate common trig values on the unit circle, look at my trig video. It's somewhere on my channel. I explain a shortcut of how to calculate it. Okay, so the cos of 120 is the same as the cos of 60 in the second quadrant. The cos of 60 is 1/2. And in the second quadrant, that's going to be negative, so it's negative 1/2. Now this will say c squared equals r squared plus, the 2 and the half cancel, the negatives cancel to make a positive, so it's plus r plus 1. Now don't get all crazy and actually find c, we don't care what c is. And the reason we don't care is c is actually s in this formula, right? And c squared is s squared, so why bother to square root? That'd be wasting time. So we've got root 3 over 4 times r squared plus r plus 1. That is the area of ACE, and it needs to be 7/10 of the area of the big hexagon. Back to how to get that again. Well, we can do that this way. Let's go ahead and say that we already know what this is, right? We know that the inner triangle ACE is root 3 over 4 times r squared plus r plus 1. And so how can we progress from there? We're going to add these 3 triangles. And we're going to use the formula half AB sine of C. It's basically 2 sides and the included angle, the sine of it, times a half. I'm not going to explain why that works in this video, but this is another fundamental concept for the area of any triangle. Okay, so then we need the area of this triangle, and we need 3 of them. So plus 3 times 1/2, A is going to be 1, B will be R, times the sine of 120. Well, if the cos of 120 is 1/2, then the sine of 120 is root 3 over 2, but it is in the second quadrant, but sine's positive there. Again, you should be able to think of that just as fast as I expressed it, and if you can't, go look at that video and try to learn how to speed up your trig skills. So it's going to be root 3 over 2, and we have this here. Now we want to figure out, this is 7/10, this is the area of the whole hexagon, all 3 triangles plus the equilateral, right? Because they're all equal triangles. Before you go crazy and start simplifying, look for a shortcut. There's a root 3 over 4 in this expression, there's a root 3 over 4 in this expression, and there's a root 3 over 2 and a 1/2, which combined is root 3 over 4. You can just multiply by 4 over root 3 everywhere and not actually write it, because we're in the business of saving time, and cancel all the root 3's over 4's. Root 3 over 4's. So now you're going to have r squared plus r plus 1 equals 7 over 10 times r squared plus r plus 1 plus 3r, which is r squared plus 4r plus 1. Again, do you want fractions running around? No, nobody likes fractions, right? Multiply by 10 and get rid of them. So you're going to get 10r plus 10 equals, and distribute the 7 at the same time, 7r squared plus 28r plus 7. Now think about what we have right now. Before we continue, maybe in the back of your mind you should have this little tickling thought, this is going to make a quadratic. And there's certain concepts we know about quadratics. We know that for ax squared plus bx plus c equals 0, there's a sum and a product of roots. Look up Vietta's formulas. I'll do a video in the future, but for now look it up somewhere. The sum of the roots of a quadratic is negative b over a. And the product of the roots is c over a, these being the coefficients of the quadratic ax squared plus bx plus c equals 0. Okay, but what are we looking for? The sum of all possible values of r. Then if we get this to a quadratic, we should start seeing this in our mind at some point in that process. We don't actually have to find r as the point. So let's keep going. Subtract 7r squared to get 3r squared, subtract 28r to get negative 18r, and subtract 7 to get plus 3 equals 0. Divide by 3 to make our lives easier, and we get this. Now, what are the sums of the value, the sum of the values of r that make this equation true? They're negative this coefficient over this coefficient. This coefficient is negative 6, so negative 6 is 6 over 1 is 6. The sum of the roots is 6. Before we move on, I want to cover one side path that you could have taken if you didn't know, say this formula or something. How else could we get the area of this right here? We could extend this side out and make an equilateral triangle out of it. A big equilateral triangle. Now how do we know it's equilateral? Well, number one, this was 120, recall? And then this is 60, and for the same reason this is 60, so that means this is 60. And since this is r, and this is r, then these will all be equilateral triangles on the outside. This is going to be one long side of 2r plus 1. All three sides are the same, so it's a big equilateral triangle. So we could say that the area of this hexagon is the big equilateral triangle's area, 2r plus 1 squared times root 3 over 4, minus these three triangles on the corners, which are all r. So they're going to be r squared root 3 over 4 times 3, right? Because there are three of them. Let's simplify this and see what we get, because this represents the area of that hexagon. So if I expand this, again, the root 3 over 4s would cancel. Let me erase this really quickly. Again, recall that this is supposed to equal 7/10 of this expression is supposed to equal root 3 over 4 times r squared plus r plus 1. Now again, the root 3 over 4s appear in all terms, so we can just get rid of them. If we expand this, you're going to get 7/10 times 4r squared plus 4r plus 1, and then it's going to be minus 3r squared. So that's going to give you 7/10 times r squared plus 4r plus 1 equals r squared plus r plus 1. If you look, that's right here. We found the same thing using that formula, and this is just an alternative path to that. So that's about it. I think I mentioned that we're going to try and find one that doesn't use law of cosines. I can't think of it right now, and I don't want to redo the whole video for that topic. Look it up on the AOPS solutions if you like. One last thing I want to point out, though, too. What if we had switched the r and the 1? What if we had put r here and 1 over here? Would it impact anything? No, all these areas would still be 1 times r versus r times 1. And furthermore, in law of cosines, these are still 1 and r. The order is just switched. So it doesn't change anything about the problem, and we can be confident that these are all the solutions that work. Next problem. All right, so the last problem of this set, which is the 2010 AMC 10A problem 20. There's more questions on the test, but I do them in sets of 5, usually for the first 20, sometimes the first 15. A fly trapped inside a cubicle box with side length 1 meter decides to relieve its boredom by visiting each corner of the box. It will begin and end in the same corner and visit each of the other corners exactly once. To get from a corner to any other corner, it will either fly or crawl in a straight line. What is the maximum possible length in meters of its path? Go back to the beginning. It's in meters. We don't have to worry about the unit. Okay, so let's make our cube. And again, to make a cube, we've made one already in this set of 5 problems. You will make the other lines parallel here. That's not very good. More like this, this, and this, and then make this line vertical, just like the ones in the front of the box, or the front of the cube. And then we'll go this way from about right here, right? Okay, and then we're going to come from the back corner straight down, also parallel to this side, and then this over here parallel to this and this and this, and this one, of course, parallel to those four there. Now because we have to visit vertices and we want to keep track of our path, we probably should label the vertices instead of just kind of randomly doing it. So we'll call this A, B, C, D, E, F, G, H. Okay, so now how can we make the maximum possible length? Well, just think. There's a couple policies or concepts at play here. The first one is that the distance from one corner to the opposite corner diagonally through the cube, basically the space diagonal of any cube, is root 3 times an edge. Well, our edge is 1, so that means it's just root 3. Further, the face, not space, but face diagonal like E to B would be root 2. That's by 45, 45, 90. So these are the lengths we're actually kind of wanting to work with more than other lengths. So let's just say we start at A just for no particular reason, just to get started. Well, you want to have as many of these as possible. And if this isn't possible, try to get this. Okay? So then A, where would you go to make a space diagonal? You would go to G. And so A to G is a distance of root 3. Now, you can't go right back to A because it says you're going to start and end in the same one and visit all of them exactly once. So from here, you're going to have to do something besides a root 3 distance. You're going to have to go a root 2 distance. I mean, you could go a 1, but that's not very good. So you're going to go from G, let's say to B, right? We'll go up to B from there. That's a face diagonal, and it gives root 2. Now, once you're here, you can go back to a space diagonal again. Go down to H. And so that will be a distance of root 3. But you can't go back to B because of obvious reasons we talked about before. So now where should you go? Don't go up to D. You have two choices. You can go to C or to F. And it doesn't really matter which one. So we will go to C. So if we go to C next, that's a distance of root 2. From here, we want a space diagonal again. We come down to E. And so that's going to give us plus root 3. And then from E, we don't want to go to F. We only have D and F left. So let's go to D because F is a shorter distance. Go to D. That's going to be a face diagonal, the root 2 variety. And then from D, we're going to go down to F. That's, again, a space diagonal of root 3. And finally, return back to A. And so if you think about it, we have traveled the space diagonal all 4 times, which is the most that you can travel it. That means the most any other length can be is root 2. We can be very sure this is the maximum length. 1, 2, 3, 4 root 3s, 1, 2, 3, 4 root 2s. That's going to make it 4 root 2 plus 4 root 3. Not that bad if we just get started and apply a little bit of logic. See you in the next video.